You know, whenever you chat with an AI, you're talking to this massive, invisible engine, right? But what's actually powering it? It turns out not all AI brains are built the same way. So today, we're going to pull back the curtain on the specialized chips that make AI tick to get to the bottom of a really interesting question.
I mean, you've totally felt this, right? You ask one chatbot a question and boom, the answer's right there, instantly. You ask another one and you're just staring at that blinking cursor for what feels like an eternity. Well, the answer isn't in the software, it's in the hardware. And it's a story of two very different chips, built in two very different times to solve two very different problems.
All right, let's dive in. Our story really kicks off about a decade ago, back when AI started to become this huge data center scale challenge. And here's the thing, the tools they had back then, they just weren't going to cut it. This was the first major AI bottleneck.
So back in 2013, Google basically hit a brick wall. They crunched the numbers and realized that if everyone used voice search on their phone for just 3 minutes a day, they would have to literally double the size of their data centers. Just think about that. Using the standard CPUs they had was just way too slow and way too expensive. So they spun up a top priority project, and in just 15 months, which is ridiculously fast in the world of chip design, they deployed a radical new solution, the first TPU.
So, this thing they built, the first ever Tensor Processing Unit, or TPU v1, it was an absolute game changer. This wasn't just a slightly faster chip. No, this was a completely new kind of processor, designed from the ground up for one job and one job only, running AI models at an incredible speed.
All right, now this looks like a lot, I get it, but don't worry about all the little boxes. The key thing to see here is just how specialized this whole layout is. See, unlike a general-purpose CPU in your laptop that has to do everything, the TPU v1 was what's called an ASIC. It's a specialist. It's a tool built for a very specific purpose.
So what exactly is an ASIC? It stands for Application-Specific Integrated Circuit. And honestly, the best analogy is a Swiss Army knife versus a MasterChef sushi knife. The Swiss Army knife can, open a bottle, file your nails, it does a bunch of stuff okay. But a MasterChef sushi knife? It does one thing, slice fish, and it does it with absolute perfection. The TPU was that custom knife, engineered specifically for the math that makes AI work.
And the heart of this custom-built beast? Its matrix multiply unit. And get this, it packed 65,000 individual math units onto a single chip. That is just a staggering amount of raw computational power, all focused on the one type of math that neural networks depend on.
And this quote from the original paper just says it all, perfectly. The whole point, the entire design philosophy was just keep that massive engine fed. Keep it crunching numbers 24/7, nonstop, with zero downtime. It was a pure workhorse.
But time moves on, right? Fast forward a few years, and the whole world of AI just explodes. The models didn't just get a little bigger, they got enormous. And with this massive shift, a totally new enemy popped up. The fight wasn't about raw computation anymore. The new bottleneck was something else entirely.
And that new enemy has a name: latency. With the rise of these huge large language models, the LLMs that power all the chatbots you see today, the main problem wasn't just how many calculations you could do in a second. No, the problem was the delay. It's that agonizing pause between when you ask your question and when the AI actually starts giving you an answer. That's latency.
And the number one cause of that latency? It's all about memory. Imagine a super fast chef in a busy kitchen. If all their ingredients are prepped and laid out right in front of them on their prep station, they're just flying. But what if for every single ingredient, they had to stop what they were doing, run down 2 flights of stairs to a giant walk-in freezer in the basement just to grab one little thing? Their momentum is totally killed. That wasted trip? That's memory latency in a nutshell.
Okay, so this is exactly the problem that a company named Groq decided to tackle head-on. They designed a brand new chip from the ground up, the Language Processing Unit, or LPU, with one single obsessive mission: to kill latency and make AI feel instantaneous. So how'd they do it? Well, let's go back to our kitchen. The original TPU stored its main data in what's called off-chip DRAM. That's the big walk-in freezer in the basement. Yeah, it holds a ton of stuff, but it's a slow trip every time you need something. Groq's LPU does something totally different. It puts a huge amount of super-fast memory, called SRAM, right on the chip itself. This isn't just a tiny cache, this is the entire prep station. Every single ingredient is right there, within immediate arm's reach. No more trips to the basement, period.
But that's only half the story. The other secret weapon is something called scheduling, which is really just a fancy way of saying, how does the chip decide what to do from one moment to the next? Think about the difference between the spontaneous improv show and a tightly choreographed Broadway play. One is unpredictable and made up on the spot, the other is planned down to the millisecond for a perfect, repeatable show every single night.
The TPU V1 was more like a really good actor hitting their marks. It was deterministic, sure, but it was still taking cues from an offstage director, the host computer. The LPU, though, it's the full-on Broadway production. This is called static scheduling. Before the AI even begins its job, Groq's compiler plans out every single step, every data movement down to the exact clock cycle. It's a completely pre-choreographed play. All the guesswork is gone, which means it's unbelievably fast and predictable.
Okay, so you might be thinking, how do you get all this speed without messing up the AI's answers? Well, Groq has this really clever trick called TruePoint numerics. It's kind of like getting the best of both worlds. Imagine you're a graphic designer working on a huge digital poster. To make quick edits, you might work on a smaller, lower quality preview. It's just faster. But every change you make is secretly being applied to the massive high-resolution master file in the background. So when you're done, the final product is perfectly sharp. That's what this does. It speeds things up by 2 to 4 times with basically no loss in quality. It's pretty brilliant.
So when you put this all together, what do you get? You get this really fascinating story, right? You have two incredibly smart pieces of hardware, but they're not really competitors in the way you might think. They're products of their time, designed to solve two very different puzzles.
Let's just break it down one last time. Google's TPU V1, back in 2015, its big problem was raw speed for the AI of its day. The solution? That walk-in freezer memory and the cued actor style of work. Now fast forward to the Groq LPU. The problem is totally different. It's all about latency for these gigantic language models. The solution? The prep station memory right on the chip and the choreographed play for scheduling. You see, the whole philosophy shifted from how many calculations can we do to how fast can we get that first word out.
And this is the key takeaway, really. It's not about which one is better or worse. That's the wrong way to look at it. They are different tools for different jobs built by brilliant problem solvers who are staring down the biggest challenge of their era. The TPU solved a throughput problem. The LPU is designed to solve a latency problem.
And that, of course, leaves us with one final huge question. Because AI is not slowing down. I mean, these models are just getting crazier and more complex every year. So what's the next bottleneck going to be? What's the next big problem that maybe no one even sees coming yet? And what will that next generation of problem solvers, that next revolutionary chip, even look like?